How will climate change impact stream flow in the upper Colorado River Basin? What happens to groundwater levels? Hello friends, Jim here. Well, climate change will reduce stream flow in the upper Colorado River Basin as groundwater levels fall, study finds. So we have an illustration of basically the water cycle, losses and gains. I'll go over that in greater detail later on. The Colorado River makes life possible in many western cities and supports agriculture that sustains people throughout the country. Most of the river's water begins as snow melt from the mountainous watersheds of Colorado, Utah, and Wyoming. A warming climate will drastically reduce these stream flows, new research finds, because there's less snow. And instead of the snow slowly melting over the summertime, if there's less snow, it quickly disappears, or if it rained during the wintertime, it just runs off. So there's less snow, there's less slow melting of the snowpack to basically recharge the groundwater and the water table. Researchers from Desert Research Institute, U.S. Geological Survey, and Lawrence Berkeley National Lab teamed up in the new study published in Nature Water. By applying warming to historical conditions for the East River in Colorado and using computer simulations to observe the impact on stream flow and groundwater levels, the scientists found that groundwater storage would fall to the lowest known levels after the first extremely dry year and fail to recover even after multiple wet periods. That's kind of important there. Groundwater storage would fall to the lowest known levels after the first extremely dry year and fail to recover even after multiple wet periods. When groundwater levels fall, stream flows are drawn into the water table instead of contributing to Colorado River flows. Also important to highlight. Groundwater levels fall, stream flows are drawn into the water table instead of contributing to the Colorado River flows. Rosemary Carroll is a PhD and a DRI research professor of hydrology and the lead author, the PI. We found that groundwater matters a lot. Even with historically observed wet periods in the model, the groundwater can't come back from a single dry water year on the end of century warming. Colorado River has been in a drought state for decades. And this has created a whole bunch of political problems and tensions, water rights, etc. around the Southwest. I'm going to avoid that. Science has been perplexed by falling river levels even in relatively wet years. In 2021, the upper Colorado River Basin reached 80% normal snowpack, but only delivered 30% of average stream flow to the river. So that disparity would, as they implied earlier, seems to be that the water went into the ground to recharge the water table and not contribute to the stream flow of the river. So the researchers wanted to examine how warming in the mountain basins may be contributing to this phenomenon. Increased temperatures altered the balance between snowfall and water availability in a number of ways, including more snow evaporation, which is called sublimation, basically going from the solid to the gas, skip the liquid phase. More precipitation falling as rain instead of snow, and more frequent melting throughout the winter. You may have some snowfall, but if it warms up, that snow melts instead of accumulating, so you get a nice snowpack to melt throughout the summer, as what used to happen historically. Past research has largely overlooked the role of groundwater and how it may buffer or intensify stream flow loss from climate change. I'm very interested in the relationship of groundwater contributions to stream flow, and that's been something her research has focused on for some time. A lot of studies indicate that in the short term, groundwater release to stream flow will help buffer drought impacts, but before the study, we didn't have any knowledge on what that would mean in the long term. Another graphic I will go over with you in a few moments. The study authors used the East River as the focus for the research because it's representative of the headwaters of the Colorado River, as well as the significant weather and water monitoring infrastructure available. Ground observations and airborne mapping measure snowpack depth and density, stream flow, plant cover, and groundwater levels, among other parameters. Historical data from 1987 to 2022 was used to create the computer model. The research team applied 4 degrees Celsius of warming to this time period in 2 ways. For one simulation, warming was applied constantly across time, while in subsequent simulations, warming is applied to each season independently. The approach allowed the scientists to examine the differing impacts of warming between seasons, presumably to see the impacts of different types of warming regimes, steady or pulse manner, is what I'm reading into this. 4 degrees Celsius is representative of the projected climate at the end of the century based on observed warming of approximately 0.4 degrees Celsius per decade in the watershed. Probably be higher. The simulation doesn't account for likely changes in vegetation over the same time frame. The study showed that consistently warmer temperatures resulted in sharp declines in groundwater levels that were unable to recover to historical average levels during wet periods. Isolating the warming seasonally demonstrated the strong impact of warmer summers on water table declines. As the atmosphere increases evaporation rates, plants increase their water uptake, soils dry out. And don't forget, the plants will also lose water through their stomata, transpiration. And then they have to further suck up more water from the ground. So you got increased evaporation that takes water out of the ground. You got plants increasing uptake, and they have an increased rates of transpiration. They were required to uptake more water. The largest declines in water table elevations occur in the subalpine forests, where conifer forests are most dense. Right? Spruce, firs, that kind of stuff. As the groundwater level drops, you lose more stream flow to the water table, Carroll says. When precipitation is low, the East River stops flowing for a portion of the summer. This would, of course, have dramatic effects on ecological health, agricultural, irrigation. By including declining water table levels in the analysis, the study found that stream flow reductions nearly double when compared to simulations that examine the impacts of climate change in the region without accounting for groundwater declines. This is because the multiple impacts occurring simultaneously, less water flows to streams from the aquifers while more stream water drained into the soil. So, this research demonstrates the need to jointly manage forests and groundwater in the upper Colorado River Basin, as well as account for the exchange of surface and groundwater in mountain basins to minimize stream flow decline under climate change. So she does these analogies to financial stuff, whatever. But So let's take a look at these diagrams here. Start with this one here. This illustration shows historical atmospheric environmental water losses and contributions. Credit Carroll et al. So you have, let's look at the inflows. You have precipitation, 947 plus or minus 176 millimeters per year. Of course, 1,000 millimeters is a meter, so not quite, you can look at this like 95 centimeters if you wish, plus or minus 18 centimeters. Now, here's the interesting thing. Of this precipitation, snowfall is about 80% of it, plus or minus 18%, while rainfall is only 20, plus or minus 6%. So it mostly comes down to snow. Well, as the climate is changing, there's less snow and more rain. So the snowfall percent is coming down, the rainfall percent is going up. So those are your inflows. Now you could have, this illustrates your snow, right? The depth of the snow. It may slide down, so you get sublimation, which is about 2%. So sublimation adds it to the atmosphere. These blue arrows this way and this way, so forth, these indicate water moving into the groundwater, into the water table, and so forth. Now you're going to have a canopy evaporation, soil evapotranspiration, right? There's going to be some infiltration of the snow into the ground. And this blue arrow here shows the uptake of plants. We have some interflow that supports evapotranspiration. Right? So, of what goes into the ground, you have an unsaturated zone, and then you have saturated groundwater. So it will flow into this to, moisten, wetten the ground, recharge the water table. So we'll get all these inputs into the ground. In addition to the sublimation, redistributing, and evapotranspiration, you're going to get some of this groundwater that will actually go directly into the stream. And you may also get some of the water from the saturated groundwater going into the stream as well. Some may go into the unsaturated zone. From the unsaturated zone, you're going to get groundwater evapotranspiration. That's about 2%. You're going to get surface runoff to the streams, another about 2%. Such as rain washing off, or the snow actually that does not percolate into the ground flows into the stream. So what they're saying, what they're finding is that because there's less snow and things are getting drier because of the drought conditions, the air is warming up, so it's going to hold more moisture, that any snow melt that is there, any precipitation that does flow, moves more to recharge the groundwater, which has been depleted, as opposed to going into the stream. So the stream levels drop, the flow rates decrease, if not stop altogether at certain times of the year. So that's what they're finding. Now, what are the outflows? Total evapotranspiration is about 50 centimeters plus or minus 3 centimeters per year. The stream flow, about 44.5 centimeters per year plus or minus 14 centimeters per year. And it's almost an even split between total evapotranspiration, about 53%, and stream flow, about 47%. So here's the fraction. Groundwater, box and whisker plots. the interflow, and then surface runoff. So let's see if I can do some quick math in my head. If I add these up, I get 946. And they say 947. So the budget is almost balanced. So that would imply that that other 1 millimeter, that's really the only difference, it remains in the plants, or is error, something like that. So that's so this is kind of like think of it as a breakdown of a budget, like showing the fate of precipitation and what's happening to it. If there was no drought, then the saturated groundwater would probably be closer to the surface. The unsaturated zone would not be too far away from being saturated, so that you would get, there'd be plenty of water here for the plants to do that, to utilize and so forth, and you would get the rest, flowing into the stream. The ground is drying out, so the precipitation, instead of going this direction, goes this direction in an attempt to recharge the ground. That results in less water going into the stream levels, river levels dropping, stream levels slowing or stopping. And there's the problem as mentioned earlier. Less snowpack, there's going to be less water available for the ground. Warmer temperatures, more evaporation. You're going to pull the moisture, the water, from the ground. Plants are going to lose more water because of transpiration processes. They pull water from the ground. You dry out, the result is you dry out the ground. You lose the moisture to the atmosphere. Warmer atmosphere can hold more moisture. Okay. Let's take a look at this diagram. This graphic illustrates how declining water tables under climate change would decrease stream flows. And this is Jeremy Snyder from the same research team of Carroll. So in the top up here is the winter scenario, and down here is the summer scenario. So on the left side are historical climate situations. The right side is what was likely to happen towards the end of the century. So this is winter historical, winter end of century scenario, summer historical, summer end of century situation. So in the winter historical, the water table is high, right? And you get nice water flow. So you have low melting, a steady supply of fresh water. With decreased snow cover, end of the century, you have earlier onset of infiltration and runoff. So you have early melt. There's probably not as much snow to melt. Now you could actually get stream levels to rise. And what they're saying is there's a gradient-driven loss from the stream. Now this is in wintertime. Okay? In the summer historical, you have a high water table, stream flow is supported by the groundwater, you got some rain, right? And you get nice levels. Summertime at the end of the century, you get increased forest and riparian, ETs, evapotranspiration. Recharge and runoff limited by low soil moisture. Groundwater is intercepted by riparian plants. Stream levels fall. So if you've noticed, right, in the wintertime, you typically have low stream levels, right? Then, right, when things melt, whatever, right, the rivers rise because you're getting the melting. You see that in springtime, right? The springtime melt, the summer melt, water levels rise and they start falling over the course of the year until wintertime they reach low levels. What they're saying is that you're going to see stream level rising in the wintertime at the end of the century, but this is due to some infiltration, but then that leaches out. Summertime is where it's going to be the highest impact. Instead of water gradually feeding the streams, the ground is dry. There's nothing left. So when you look at it, it's the summertime that seems to be going to be the most adversely impacted. The plants are going to intercept whatever they can, leaving less to go to feed the streams. That's going to impact the aquatic organisms in the streams and rivers, the fish, the invertebrates that live there. So that is what's happening. So what they are saying is that there's going to be, overall, by the end of the century, there's going to be less water in the ground table. In the ground, there's going to be less groundwater. The water table is probably going to start dropping. It's going to be less water in the groundwater because of declining snow, more runoff, and whatever does percolate into the ground is going to be used up. As the air warms, it's going to, due to evaporation, it's going to pull more water out of the ground. Plants are going to use up what's left. They're going to lose water through the stomata, pulling up more water. So the result is you're going to lose a lot of water from the ground, and therefore there will be less water available to feed the streams, and then stream levels drop, and the flow rates drop. That's what they are finding. This is another example of what's happening as the planet warms. Now, it's very possible that whatever moisture goes into the atmosphere, that it pulls out of the ground, depending on the wind conditions and directions and the atmospheric flow rates, that moisture could end up moving to another location, and therefore that water is lost. As opposed to, okay, you build up the moisture, the clouds kind of stay put, and it rains, returns the moisture to the ground. It may move on. A lot depends on the pressure and temperature gradients. But that's another possibility, in which case then that water is lost for good. And if you have prolonged droughts, as that what they were finding here, the situation becomes dire. That leads to increased plant mortality, and if the plants die, well, there goes the whole ecosystem. So, more concerning news. Thank you for your time.